Spectrophotometry is an analytical technique used to measure how much light a chemical substance absorbs by passing a beam of light through a sample solution. It's based on a simple principle. Different substances absorb light at different wavelengths, and the amount of light absorbed is directly related to the substance's concentration. Beer's law is also known as Beer-Lambert law. It provides the fundamental principle for spectrophotometry, and it describes the relationship between the concentration of a solution and how much light it absorbs. In simple terms, it tells us that the more concentrated a solution is, the more light it absorbs when light passes through it. Beer's law tells us that absorbance increases linearly with concentration, and if you double the concentration, the absorbance doubles, provided that the path lengths and wavelengths remain constant. This linear relationship is extremely useful because it allows us to determine an unknown concentration simply by measuring absorbance and comparing it to a calibration curve built from known standards. Spectrophotometry is a powerful analytical technique used across many scientific disciplines such as chemistry, physics, biochemistry, material and chemical engineering, and clinical applications. It is a method used to measure how much light a chemical substance absorbs. This is done by passing a beam of light through a sample solution and measuring the intensity of light before and after it passes through the sample. This measurement can also be used to measure the amount of a known chemical substance. By understanding how substances absorb light, we gain insight into their concentration, purity, and behavior. Spectrophotometry is non-destructive, fast, and highly sensitive, making it ideal for routine analysis and advanced investigations alike. Beer's law, also known as the Beer-Lambert law, forms the backbone of spectrophotometric analysis. It allows us to quantify substances based on how they absorb light. Let's walk through the diagram. A beam of light with intensity I0 enters a cuvette containing a sample solution. As the light passes through, some of it is absorbed by the solution. The remaining light exits with a lower intensity I. The difference between I0 and I reflects how much light was absorbed. This absorbance increases when the path length B increases, meaning the light travels through more of the solution. The path length is the distance that light travels through the absorbing sample, usually the internal width of a cuvette. The absorbance also increases when the concentration C increases, meaning more solutes are present to absorb the light. So, if you double the concentration or the path length, the absorbance doubles too. This linear relationship is what makes Beer's law so useful for quantitative analysis and can be expressed mathematically like this. Absorbance A is directly proportional to both path length B and concentration C. Proportionality constant A can be used like this to make the mathematical expression of Beer's law, capital A equals ABC. Lowercase a is also called the molar absorptivity. The molar absorptivity depends on the chemical nature of substance, but does not depend on the concentration. Beer's law tells us that absorbance increases proportionally with concentration, assuming constant path lengths and molar absorptivity. To determine the concentration of an unknown solution, we first need a calibration curve. It is a graph that plots known concentrations of a substance against their measured absorbance values. This is an actual data set that shows how the observance of a copper 2+ solution changes as its concentration changes. As the concentration of the standard solutions of CO2+ increases, their observance also increases. This can be plotted on an Excel spreadsheet like this: observance versus concentration in molarity. This plot is called calibration curve, and it is a graph that plots the observance of standard solutions against their known concentrations. Keep in mind that the vertical axis is for observance while the horizontal axis is for concentration. We may use the equation for the best fit line to determine the concentration of an unknown solution. The y can be replaced with observance A, and the x can be replaced with concentration C. The equation can be rewritten with respect to concentration C like this. Here is an example on how to use the equation to determine the concentration of an unknown solution. The observance of a Cu2+ solution with an unknown concentration was measured to be 0.786. What is the concentration of Cu2+ in the solution? We will use the modified equation above. Plug the observance value of the unknown Cu2+ solution into the equation. The concentration of Cu2+ in the unknown solution is 0.0930 molar. Now, let's try an online activity to reinforce our understanding of spectrophotometry and Beer's law. Log into the course site on D12. Click the Content tab at the top. In the left menu, open Lecture Material. Then select the module titled 05 Beer's Law. Under that module, find Lab 05 Beer's Law and download the worksheet. Complete the worksheet as you work through the online simulation. Return to D12 and under the same module, open Simulation Beer's Law. In the simulation, select the Beer's Law window. Select copper 2 sulfate from the solution list at the bottom. You may adjust the concentration of the solution using the slider at the bottom. Use a roller at the bottom left corner and adjust the path length or width of sample cuvette. Turn on the light source on the left by clicking a red button. Drag the meter and place it behind the sample cuvette where the transmitted light passes. Make sure that observance is selected. Select Variable in the Wavelength panel. You can change wavelength. When you have finished exploring, open the downloaded worksheet and follow the step-by-step instructions and complete the worksheet.